Allow me to introduce our first keynote speaker. Professor Martin Grohe is a full professor in RWTH Aachen University, Germany. There, he is the chair of Informatics 7, the group of logic and theory of discrete systems. He is a computer scientist known for his research on database theory, mathematical logic, the logic of graph, and many other interesting topics. He has won the Heinz-Meyer-Leibniz Prize awarded by the German Research Foundation in 1999. He is also elected as ACM Fellow since 2017. So without further delay, please start, Dr. Grohe.
Thank you, Rian, for the introduction, and thank you very much for inviting me. It's a pleasure for me to speak here because the topic databases and machine learning is very interesting to me, and I'm trying to do some work there. My talk today will be from the perspective of a theoretician, as you'll see, but I hope it will be interesting for you anyway. Okay, so can you see my slides now?
Yes, we can see them.
Good. So I think let's just get started. So I will speak about vector embeddings of graphs and relational data. And okay, so vector embeddings, I suppose you all know what they are. We have some objects from an arbitrary class, and we want to map them to a vector space. That's what we call a vector embedding. So we have a space of objects. In this case, these are just words, and we want to map them to some vector space, as you see there. And I think word embeddings are what is best known. So it's, I think, already 10 years ago then when word2vec came up, and that caused a lot of interest, and well, things have progressed from there. Still, that may be the basis for a lot of thinking about vector embeddings, and in some way also important for us here. So the goal is to embed not just embed the objects arbitrarily, but in such a way that the semantics of the objects is reflected in the embedding. So we want to map semantic relationships between the objects to geometric relationships between their images. Now, that may mean a lot. The most important thing is that distance, semantic distance, similarity between objects is somehow correlated to geometric distance in the latent space. That's what we call the space where we embed to. And that's an interesting point in some way. It seems almost trivial, but there are several things to think about. First of all, it's not always clear what semantic distance might be. Think of the objects, and this is what we're going to talk about today, as being graphs or relational structures of something like this. It's not really clear what makes two graphs similar. Okay, so it's not clear what the right distance is, and we may even turn this around. We say we just embed them in a meaningful way, and that gives us a distance on the graphs. And the second thing is geometric distance. When I say it like this, we would usually think of something like Euclidean distance in the vector space, but it could be something more complicated. For example, we can imagine that within this large vector space, all objects are mapped to some manifolds, to a particular shape, and then the distance is some geodesic distance on that shape rather than just the straight line distance in the space. So there are many interesting questions around this, but these are questions that don't have to concern us now. so for us, I think the main thing is we want to embed objects in a way that semantic corresponds to geometry. And why would we want to do this? Well, the probably most important reason is just that standard machine learning algorithms operate on vector representations of data. So we need to generate vector representations. We can also cast this more generally by saying that by mapping discrete objects like graphs or words to a continuous space gives us a lot of new mathematical techniques that we can use, ranging from linear algebra to something like functional analysis. Okay, so what are we going to embed here? I was saying we're graphs, relational structures, but we need to distinguish between two things which are related but not exactly the same. And the first is node embeddings. And I guess in the realm of graphs, these are best known. So the objects that we want to embed are the vertices of a graph, okay? Graphs can be directed, labeled, weighted, whatever we want. That's the case throughout my talk. Although when we have directed graphs, we have this interesting issue that on how to represent the direction of the edges in the embedding space. But anyway, typical applications of node classification, node embeddings are classification tasks in social networks or link prediction in knowledge graphs. The second is we can embed the whole graphs. Okay, so you see all these little graphs. Now, a whole graph is mapped to a point in the vector space. And again, the graphs can be directed, labeled, whatever we want. A typical application of this type of embedding would be classification and regression tasks on chemical molecules represented by graphs. And actually, this is the part I've worked on more. I have some collaboration with chemical engineers where we use embedding techniques, machine learning techniques to design regression models for actually biofuels. Okay, so let's compare node embeddings and graphs embeddings. First of all, we embed the same basic structure, graphs. And in fact, if we have a graph embedding, we can apply it to the neighborhood of the nodes of a graph, and we get a node embedding. But there is a very important difference, and that has a lot of impact on the embedding techniques that we use. The nodes of a graph have explicit relations between them. They have a distance, shortest path distance in the graph. So if we embed nodes, we usually want to take this distance into account. If we just embed graphs, well, there's no relationship between them, at least no direct relationships. They are only semantically related. So that's something to keep in mind. And there's a second issue when we want to learn embeddings. For node embeddings, typically we have a fixed graph, maybe a large social networks, and we want to embed the nodes of that graph. Whereas when we embed graphs, we're not embedding graphs from a fixed set, but we do something that we want to apply in principle to all graphs. Well, often the applicability domain will be restricted. So when we train something for chemical molecules, we can only meaningfully expect it to be applicable to molecules. But in general, we want to have an embedding that also can be applied to unseen graphs, which for node embeddings is often not the case. Similarly to word embeddings, we usually have a fixed vocabulary that we want to embed. Okay, then from graphs, we can go on to structures of higher arity. And I think in a database context, this is very, very interesting. So node and graph embeddings have been studied quite intensely and for a long time. embedding techniques have been extended in particular to knowledge graphs, that's binary relational structure. They have also been extended to general relational structures and to simplicial complexes and things like this. But this work is much more recent and less is known, I would say. There's still, it's much less clear to me what to do there. There is some work now, but I think there still is a lot to be done if you go beyond binary relations. And this has interesting applications in many different directions, but certainly databases is one of them. There's a second point that I also find extremely important, and that is that we shouldn't treat graphs as being fixed. Graphs are dynamically changing over time. And in particular, if we think of a database context, we want to embed a database, but then the database may change. We may add or remove tuples and so on. And what we want to avoid is to recompute the entire embedding after each change of the database. Okay, I'll speak a little bit about this in a few minutes. So now I'm a theoretician mainly, and I'm interested in developing a theory of vector embeddings, which I don't think exists really. So vector embeddings allow for a quantitative analysis of discrete data like graphs using machine learning algorithms, but also mathematical techniques. I've said this before. Another nice thing is that vector embeddings allow it to integrate data from different sources. We can all map them all to a common latent space. But in many ways, we don't understand them very thoroughly. We know how to apply them, but we don't really understand them. We don't really know how to approach different areas, different contexts, and so on. And I think it's worthwhile to study them in a more general perspective and just using the tools and methods of theoretical computer science. And to some extent, that's the context of this talk and my thinking about this, although I'm often also interested in just very specific applications, but I think both needs to be done. So when we want to do theory, what are the questions we want to ask? And maybe that's a key slide for me. I have much more questions than I have answers. Well, the first that come to mind are questions about algorithms and complexity. Can we compute the embeddings efficiently? That's something we usually take care of in practice, but it can be difficult if we want to represent very complicated features. We have to think about how we actually compute them. But then there's another very interesting question, and that is, suppose we have our embedding and now we have points in the latent space and we want to invert the embedding. We want to reconstruct graphs or data from their image in the latent space. And this is something that happens in many applications. I stumbled over this over and over again. So how do we do this? That's not clear at all. It's also not clear in practice, I think. There are some approaches, but they don't work too well. Why is it an important question? Think of it this way. We have some measurements on a graph. That gives us a vector embedding. Just take the individual measurements as coordinates in a vector space. And now we want to reconstruct a graph that somehow gives us these values. How do we do this? It's not really clear. The second range of questions is more rooted in logic and semantics. So what is the semantical meanings of embeddings? What features of the objects do we actually capture? What does it tell us about the objects? These are vague questions, but to some extent, these are the most important questions. And techniques from logic may help us to answer them. So we can ask which properties of a graph are preserved under the embedding, which can be, if we just see the embedding, which properties are still present there and which just disappear. Or we can phrase it differently. Can we answer queries directly on the embedded data? For example, imagine we integrate data from different sources, map them to a common space. Then in some sense, we have a view on our database, and now we want to answer queries against this view. Well, of course, the view is quite unusual, and it's not clear if we can do this and how we do this. And we probably can only do this approximately and probably only probabilistically, because the embeddings typically have some randomness in them. So what are the right notions of approximate query answers here? These are questions I find extremely interesting, and I don't think anyone has good answers to these. And then, of course, something more obvious, but still very relevant is, now if we have different embedding techniques, how do they compare? Do they induce the same or similar metrics on the graphs? Do they induce the same topology, which you can see as a qualitative form of metric, if you will? Okay, so these are the questions I'm interested in. And now let me be a bit more specific, talk a little bit about embedding techniques that are known. I will talk a little bit about some recent work we have been doing, and then towards the end of the talk, I'll speak about a general approach to computing embeddings based on homomorphisms and counting homomorphisms that I think captures a lot of what is happening in embeddings and gives us a good way of understanding them. All right, so maybe the classical technique for computing node embeddings are entirely based on a graph metric, and basically they are just trying to approximate the metric or preserve the metric as well as possible in the vector space, just using linear algebra. So let's say we have a graph, we can define a similarity matrix on this graph based on the metric, and typically it's done in this way. We take x to the minus distance between nodes as their similarity. So identical nodes have similarity 1, and if the nodes are further away, their distance quickly goes down, their similarity quickly goes down to 0. Often here we put some constant as a normalization factor, or yeah. And now we just want to compute a low dimensional factorization of this similarity matrix. That's a matrix, say, a number of nodes or node set by K matrix, such that the matrix times a transpose approximates the similarity matrix with respect to some matrix norm, and then we can see the rows of the matrix to define an embedding of the vertex set to R to the K. That's why we chose the dimensions like this. And the inner product between vectors approximates the similarity then. That falls out of this term here. Okay, so that's a classical technique that has been known for a long time and applied in many contexts with variations, of course. The second technique is somewhat more recent, although by now also well known. It's based on random walks in graphs. And the idea is to compile a list of random walks, not too long usually, and then treat them like sentences in natural language with the nodes of the graphs as words. And then use word embedding techniques, the skipgrams of word2vec to compute the embedding. Okay, so node2vec is the best known example based on this idea. Okay, another approach that has, I think, dominated the discussion in recent years is graph neural networks. So graph neural networks are a deep learning architecture for graphs. Basically, what we learn is message passing networks on the input graphs. So here we have a graph, and during inference, when we run the neural network, every node has a state, which is just a vector, and then they pass messages depending on their states, update their states. We run this for a couple of rounds. Okay. And then in the end, we have some vector embedding. Every node is mapped to its state. Or maybe we apply some readout function to this. Okay. So that just encodes an embedding function. And the interesting thing is, and the point I'm making here is the GNN gives me a way to compute the embedding, and I can apply it on any graph. So techniques like node2vec take the nodes of a fixed graph and then compute an embedding for these nodes, just like a word embedding, which is applied to a fixed vocabulary. This GNN I can apply to an unseen graphs and compute an embedding for the nodes of that graph. Okay. So one way to phrase this is to say that a GNN provides an inductive node embedding. The other methods, both the matrix factorization and random walk techniques, are transductive. This terminology, I think, is from this paper by Hamilton, Ying, and Leskovich. And the last point is we can aggregate the vectors of all nodes, and we can also use it to compute graph embeddings. Again, here it's important that we can apply the GNN to all kinds of graphs. Okay, so these are a few techniques. Oh, the one last one, also very important in the graph learning literature, and basically the main technique before graph neural networks came up are graph kernels, which still provide very good results for machine learning tasks on graphs. So kernels basically have implicit vector embeddings, but kernel methods then only need to access the inner product between the vectors. So often we don't have to compute the embeddings. And that means we can even take embeddings that map to infinite dimensional spaces. That's interesting here. Okay, so the kernel trick, as it's sometimes called, is to use this inner product without ever computing the vectors. And in many settings and for many kernel methods, we can do this. Okay, as I said, graph kernels are widely used for machine learning problems on graphs. And well, there's many different types of graph kernels based on comparing random walks, as we did in node2vec, counting small subgraphs, the Weisfeiler-Lehmann algorithm that you may have heard of. What I find very interesting at this point is that in principle here, we can even deal with infinite dimensional embeddings in a computationally meaningful way. That's just something to keep in the back of your head. So I want to quickly talk about some recent work we've been doing on embedding relational databases before I go on to the real theory part. And this addresses some of the questions I raised before. We want to embed relational data, and we want to do this for dynamically changing databases. Okay, so our goal here is to embed the tuples of a relational database. And we want to be able to adapt the embedding to dynamic changes in the database without recomputing the entire embedding after each change. And by the way, this is not only a computational issue. A second issue is that when you use exactly the same algorithm, apply it to the same data twice, you do not get the same embeddings usually. Because the embedding techniques have randomness in many places. Actually, we studied this empirically. The embeddings can look drastically different. And that's also something you want to avoid. And that's a reason why, another reason, in addition to the computational problems, why you don't want to recompute the embedding all the time. Okay. What we want to do is take into account prior knowledge of similarity between values and dependencies between relations. So, for example, if the values are just real numbers measuring something, temperature measurements, then we have a natural similarity on them. If they are words, we may use a similarity, for example, that we get out of the word embeddings. And we want to incorporate this. And another thing we want to incorporate, and that distinguishes our work from a lot that is typically done in machine learning, we want to look at a whole database, many relations at the same time. And we want to somehow include schema information. We want to, in particular, include foreign key constraints. Okay, and then what we came up with a method I'll briefly explain, and we evaluated on downstream machine learning tasks like column prediction. Okay, now there's really not that much that has been done in this direction. In particular, coupling relational and dynamic. I'm not really aware of any work. Certainly, at the time we wrote this was last year, we couldn't find anything in that direction, although I realize this is all fast moving, so maybe now there is something. So what we did as a baseline approach is something based on Node2Vec. We found that if we just embed the tuples of a database in a static context, then Node2Vec applied to some graph representation of the data works very, very well. And basically, we devised a dynamic version, which works in a fairly naive way. When we get a new tuple, we retrain the embedding, but keep the old vertices fixed, frozen, right? So Node2Vec seemed to be a good candidate because it works very well in the static context. And by the way, we also worked with graph neural networks, which I really like, and I've done a lot of work with graph neural networks, but for this, they performed very poorly, much worse than Node2Vec, which is sad, but that's what we found. So that didn't work. Now here's our approach, and it's slightly different. It combines well, database kind of ideas with an embedding technique that originates in knowledge graphs mainly. We call this forward. And basically what we do is we sample random walks that follow foreign key constraints in our database. And then what we learn when we train our model is a vector embedding of the tuples of the graph plus a metric for every type of path that we have sampled. So the type of the path would be which attributes we find, which foreign key constraints we use, and so on. Okay, or you could also call it the schema of the path. Okay, and for every type of path, we learn a metric, a distance measure, and we represent this by a matrix, which basically defines an inner product on the embedding space for the tuples. Okay, and then the objective towards which we train is to have endpoints of a path close together with respect to the matrix, to the metric for this type of path. So we learn embedding and metrics together, and that's our objective that we encode in a loss function. Okay, and now the nice thing is the way we set this up, when a new tuple later enters the database, we can determine its position just by solving a system of linear equations, which basically encodes the distance constraints. Okay, and the idea this is based on is a knowledge graph embedding technique going back to this algorithm called Rescal due to Nickel, Trest, and Kriegel. Okay, and the nice thing, these are some experimental data. I don't want to talk too much about this, but what we found is that the embedding works very well with respect to the downstream tasks. That was column prediction. Even if we train on a relatively small fraction of the data and then add tuples as we go dynamically. So if we only have 50% of the data on which we train and then add the remaining tuples one by one, we still get a model that performs very well, which we found kind of surprising. So our method is basically the blue line. We should also see that the Node2Vec dynamic version still performs reasonably well. And I find this quite surprising that the performance, doesn't degrade much from training on all tuples of the database to just training on about half of the tuples. Okay, let's leave it there and let's spend the last couple of minutes on theory. I want to talk about homomorphism vectors and homomorphism embeddings. So what's a graph homomorphism? It's a mapping between the vertex set that preserves edges. So here we have an example, two graphs. This would be a homomorphism. We map the middle point to the corner and its three neighbors to the neighbors of that point. Here's another homomorphism. This time we map the middle point here and two of the neighbors we map here, the third neighbor here. So embeddings don't need to be injective or anything. They are just mappings. All we need is that edges are mapped to edges. Okay. And now we want to count homomorphisms. Okay. So hom of Fg is the number of homomorphisms from F to G. So here's an example. We have the same graphs as on the previous slide. We count the number of homomorphisms. We find it's 70, and the way we count is basically for the midpoint for all four, we count how many embeddings there are. So for example, if we map this middle point to the upper left corner, for the three neighbors, for each of them, we have two possibilities where to map it. So that accounts for the term 2 to the 3. Now here for each of the neighbors, we have three possibilities. So we have 3 to the 3 and so on. If we add this up, we get 70. More generally, when we have a star with k leaves, okay, that would be a star with 3 leaves. If we have k leaves and arbitrary g, what we get as the number of homomorphisms is this sum. Sum over all vertices, take their degree, raise it to the power of k. Okay, that generalizes the little example, but it shows us that we get meaningful information out of these homomorphism numbers. And that's my point. The homomorphism counts give us very relevant information about the graphs. They are relevant features. So as special cases, if we take the star with 0 leaves, we just get the number of vertices. If we take a single edge, we get twice the number of edges. If we take the general stars, we get information about the degree sequence, but we can get a lot more. Okay, so what we can do is we can now view this as a graph embedding. So for a class of graph, for example, the class of all stars or all trees or paths, whatever we want, we can map a graph G to all its homomorphism counts from graphs in F. Okay, and that gives us a vector embedding. We have all these features. Now, when we want to use this in practice, we probably take logarithms here, but right now this doesn't make a difference. Okay, now here, this notation, all I use for the class of all graphs. And now if we want, we can define an inner product on the vector space we map to. We don't have to go through this, but we get a nice vector space where we also have a metric. It's an infinite dimensional space if F is infinite dimensional. If we take finite F, it's just a finite dimensional one. So here's an example. I took all these graphs, computed the embedding with respect, well, the hom F for F consisting of these 3 graphs. So essentially what I count is number of vertices, number of edges, and number of triangles, scaled slightly differently. And what I find, for example, this and this graph, the green and the orange one, are mapped to the same point, 10, 20, 0. Okay, so that's something we can do. And now an interesting notion that has been studied a lot in recent years is homomorphism in distinguishability. Mapping 2 graphs to the same point. And that work kind of illustrates that these homomorphism counts extract very relevant information from the graphs. So an old result of Loba says 2 graphs are homomorphism indistinguishable over all graphs, if and only if they are isomorphic. And now for trees, we have something very interesting. We look at homomorphism indistinguishability over trees. Okay, then 2 graphs are indistinguishable if and only if they are not distinguished by the one-dimensional Weisfeiler-Liman algorithm, if and only if they are not distinguished by a sentence of a certain logic. First of all, logic with counting, restricted to just 2 variables. This part is interesting, and when we think of answering queries on the latent space, here we have an algebraic description. The graphs are fractionally isomorphic. And finally, this is all equivalent to the graphs not being distinguishable by a graph neural network. So we have a far-reaching connection between things that seem completely unrelated. Okay, we can extend this to graphs of bounded tree width. And actually, we have many more results along these lines for other classes of graphs from which we count homomorphisms. For cycles, we get co-spectrality. For paths, we get a variant of fractional isomorphism called, also related to the solvability of a system of linear equations. We can generalize this to bounded path widths. We can look at graphs of bounded tree depth and get a logical equivalence on the other side. And we can look at homomorphism counts from planar graphs corresponding to something known as quantum isomorphism. So what these results show is that homomorphisms capture very interesting aspects of graphs and map them to a numerical domain. We also did some experiments with this. We took the homomorphism counts for simple graph classes, some trees, some cycles. Actually, we took logarithms to avoid very large numbers, and then train standard machine learning models on them and try to do graph classification. And the results were very good. This, which shows that also from a practical perspective, we kind of extract the right information, although we also should say that the homomorphism counts tend to be hard to compute. So in practice, that's a problem, of course. They are related to graph kernels, to motive counting, and also some interesting theoretical work. And that basically brings me to the end. Let me just show you a few more research directions. One thing we're looking into is study the relation between graph metrics and the homomorphism counts. We are looking at designing reconstruction algorithms. I discussed this before. We try to find vector embedding for even more complex objects, say dynamical systems or processes. And there's still this key issue of developing a better understanding of the semantics of vector embeddings. Okay, that's it. Sorry I ran late, and I'll be happy to answer your questions now.
Thank you very much, Dr. Grohe. It's a really interesting theoretical talk, and thank you for bringing us all the newest state-of-art theoretical results. And actually, personally, I have so many questions, but to leave other people space, I will just ask 3 of them. So to begin with, I heard a very interesting idea you talked about data integration, because your vision, this idea I have never heard from anywhere else. So I want to ask a little bit more. So in traditional way of doing data integration, we have multiple sources. Then each of them, we describe them by their source schema. Then we somehow create a central representation, a global schema or media schema. So you said somehow we can replace this view as embeddings. So
yes, well, it's really just an idea I'm having, and this came up in a context where we didn't really have nice relational databases, but really data from funny sources, if I may say this. And that then I realized that really when you compute an embedding, in principle, you can map very different objects. You can even map relational data and processes to the same space and try to find relationships between them in this space. And that depends on how, of course, how you compute the embedding. It's just an idea, but I think it's definitely an idea worth exploring, because it's to some extent less complicated than standard data integration tasks. Of course, you also lose a lot. You introduce a lot of imprecision in the process. So it really depends on what you do. You will only get a high-level view on your data, but that, I think, is really an option. And I kind of believe this may work. So we have various projects where we try to pursue this, although we never really started.
So for me, then this is basically you are talking about a new type of data integration system that can work for machine learning algorithms, and it can integrate not only relational, maybe JSON, XML, but even like images, videos, audios.
In principle, yes, that's the idea.
And that sounds a really good vision. Another question is regarding all the like graph neural network methods, because recently I'm doing a survey on a lot of data lake papers. I realized many people try to use graphs already. Like for example, you gave a lot of like 100 tables. I use the column of table as nodes, then their relationships, for example, primary key, foreign key, functional dependencies or semantic relationships as edges. Then would you say in principle, if I already have some kind of graph in my system, then it is possible for me to apply GNN methods to?
Yes, I mean, that's also when we worked in our forward thing with relational data, we also represent them as graphs in some form. In that context, unfortunately, GNNs didn't work. And I mean, with GNNs, it's two things. They do not always work. I mean, they are kind of overrated in some way. And if they work, usually it takes a lot of effort and a lot of fine tuning to make them work. And then we have some applications where they really do extremely well and surprisingly well. I don't want to put them down. I'm working on them myself, right? And I really like that. But it's not always clear that they work best. And another thing is they are often very sensitive to the specific representation of your objects of graphs you use. And sometimes it's not the obvious representation that works best. That's also something we found just in our more practical work.
Okay, so basically you are saying there's still much research work to be done if we try to apply GNN in our own representation.
Yeah.
Yeah, okay. Thank you very much.
Question there.
Oh, can I ask you a question? Great talk, by the way. And we've had also experience with GCNs, RGCNs, and GNNs. It's very tricky, right? It's very tricky. But I had a question. It's really interesting to see you use the knowledge graph, like node to vec representations or the vector embedding approaches. So what is like the key difference for you between a relational database and a knowledge graph, or how much is it just how much do we go look at ICLR, which was two weeks ago, look at the a billion papers about embeddings and say, oh, we can apply these to relational databases? And that's kind of what I was thinking in the back of my mind the whole time.
I think, okay, in principle, there's not much of a difference. In practice, it's tricky. And you know, there is something to higher arity relations. I mean, they encapsulate relations between more objects, and it's, you know, yes, you can translate it into graphs without losing information, but that doesn't mean that your machine learning models can easily retrieve the information you hid in your encoding. So I think the main difference is more just pragmatic, that for me, okay? But I'm not so sure what the best way of dealing with this is. So for example, something different we did is we worked on solving constraint satisfaction problems with graph neural networks. And it took us a long time to find a good way to generalize from binary constraints to higher arity constraints. And the way we came up with in the end, we're currently writing the paper, is not at all intuitive. So it requires some thinking and some experimenting. And I think that's the main difference. So
no, that makes sense. Thanks.
To make too much out of it, but it's a practical difficulty, certainly.
Thanks.
Okay, thanks again, Dr. Grohe, for your wonderful talk.